So what is statistics? When we are talking about statistics, we're actually talking about a branch of math. Statistics is a branch of math. So in this case, when you're dealing with statistics, it means that we have to follow some steps. In step 1, we start asking a question. In step 2, after asking the question, we start collecting the data. After collecting the data, we are interested in graphing the data, how to visualize the data. Remember that we're using histogram, bar graph, to visualize the data. There are other methods to visualize the data. Histogram is very useful when we are dealing with numerical data. For a histogram, we had some little bars next to each other. There is no gap in between these bars, and we create a histogram. For a bar graph, however, you have some bars, but there are gaps in between those bars. So if you want to visualize a bar graph, the bar behaves like this. You see gaps in between these bars. We use histogram for numerical data. And we use bar graph for categorical data. Well, after visualizing the data, we're interested in analyzing the data. Analyze the data. How do we analyze the data? You're interested in finding the center of the data and also variability. What are the examples of center of the data? Examples of center are mean, mode, and median. When it comes to variability, we would like to know what is the range, what is the standard deviation. In our last step in defining statistics, we are interested in making inferences, make conclusions. In first part of statistics, we talked about different types of study, how to ask a question, how to collect data, how to visualize the data, and then what is the analysis of our data. In the second part of statistics, our focus is on making inferences. When we are defining the mean, we take all the data, add them together, and divide by the number of values in our collection. So mean of the data, when we are talking about the mean, we take all values in the collection and add them together, sum the value, all values and then divide by the number of values in the set. However, when we are talking about the mode, mode is the value with the highest frequency in the collection. The value with the highest frequency. The number that is repeated the most. So the mean of the data is always a unique value. You might have more than one mode, but the mean is unique. We only have one mean. The mean is unique. Mode, but we can have more than one mode. So we talked about the center, mean, mode, and median. Mean is unique. We can have more than one mode. And when it comes to median, median is the middle number. Median is the middle number. And it's also unique. What about the variability in our collection? How do we define range? How do we calculate standard deviation? What is the definition of range? The range of the data is the maximum minus the minimum in our collection. However, mean doesn't take into account all values. It only takes the minimum value and the maximum value. It doesn't take into account the rest of the numbers. That's why when we are talking about variability in our data, we are interested in finding the standard deviation. So what is standard deviation? The range is maximum minus minimum, and the standard deviation gives us a measure of variability. It gives us the average distance between the data and the mean. So when you're talking about variability in your collection, we are mainly interested in finding the standard deviation. It's a better measure of variability than the range. Why is that? Range only takes two values. Standard deviation takes into account all data in your collection. Sampling distribution for proportion. First of all, let us go back to algebra. How do we find the proportion? Let us have a bag of M&Ms, so we have a bag of candies. In that bag, we have 1,000 candies. What are we going to do? We're going to randomly select candies out of this bag without looking at the candies inside the bag. So this is our bag with candies. We have 1,000 candies in this bag. And we're going to randomly take candies out of this bag. So when we start taking candies from the bag, we want to know how many blue candies are inside this bag. We want to know how many blue candies are in this bag. So I'm going to take my first set of candies out of this bag. So in the first set, I have 10 candies. In these 10 candies, I see 2 red candies, 2 blue candies, 2 red candies, and also I have 6 green candies. So question is, what is, so in this set that I took out of 1,000 candies, I have 2 blue, 2 red, and 6 green candies. What is the proportion of blue candies? What is the proportion of red candies? And finally, what is the proportion of green candies? How do we form these proportions? What is the definition of proportion? The proportion of blue candies. How many blue candies do we have? 1 and 2. 2 out of how many candies in total we took out of this bag? 10 candies. So the proportion of blue candies is 20%. So in this small collection, we have 2 candies which are blue, and it comprises 20% of the candies in the small bag. What about red candies? The same process. For the red candies, we have 2 divided by 10, which is again 20%. However, for green candies, we have 1, 2, 3, 4, 5, 6 green candies out of 10, which is 60%. That's how we calculate the proportions of different colors in the bag. Well, now we are interested in knowing what is the proportion of all blue candies in this bag. In our next attempt, we're going to take out another bag of candies. Take a look at this. So this is my first bag. I took out 10 candies. Now in the second attempt, I'm going to take out 10 more candies. In this small bag, I have now 3 blue candies, 1 red candy, and I see again 1, 2, 3, 4, 5, and 6 green candies. What about now? What's the proportion of blue candies? The proportion of blue candies is now 3 out of 10. In the first bag, it was 2 out of 10, 20%. Now it is 30%. You take out another set of candies, 10 candies, and you see, well, I end up with 1 blue candy, 3 red candies, and then 6 green candies. So what's the proportion now? The proportion of blue candies is 1 out of 10, which is 10%. In statistics, we continue this process. We repeat this process as many times as we can by using the technology. Why is that? Because we want to get a very precise outcome. So when we are making inferences, we have the correct answer. So that's how we calculate the proportions. Exploring simulated distributions of sample proportions. In last class, you learned about sampling distributions of sample proportions. We learned that the mean of sampling distribution of sample proportions is equal to the population proportion. We also learned that the variability of sample proportions depend on sample size. Sample proportions from larger samples tend to be closer to the population proportion than sample proportions from smaller samples. In this lesson, we use simulations to examine how the spread and the shape of distributions of sample proportions are affected by sample size. This will prepare us for the type of thinking that is involved in statistical inference. Let's take a look at this example. Global warming. The Gallup organization conducts surveys in many countries to obtain categorical and quantitative information about how people feel about important issues. One important topic that Gallup investigates is people's opinion about climate change. Gallup surveyed people in the United States during March 2014 and found that 16% of Republicans worry a great deal about global warming. For this activity, suppose the Gallup result, which is 16%, is the population proportion of Republicans who worry a great deal about global warming. We will use computer simulation to explore what happens if you repeatedly select random samples of various sizes. So this is the report that is given to us. Guys, take a look at this report. First, we use n equals to 20. These are your sample sizes. When you take sample sizes of size 20, you can form some proportions. What is the percentage? How many people are worried about global warming? This data set and the graph is coming from an Excel simulation. So let's see, what do we have here? Here, P, or the proportion, is 16%. We use P to represent the population proportion. We use P hat to represent sample proportion. So when you see P with a hat on top of it, it means that you are dealing with sample proportion. So let's see, what do we have? On the horizontal axis, we have the percentage: 0%, 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, and 90%, and eventually 100%. Look at the data. The data are highly skewed. The tail of the graph is on the right-hand side. So it seems like your graph is skewed to the right. If we shift this, if we repeat, we can shift this graph and create a normal distribution. So what does it tell us? It tells us, hey, 0% count as less than 50. 10% count more than 200. This is the frequency that you have, everyone. Then you have 20%, which is around 200. We have 30%, which is around 50. 40% count like it's very small, like 10, 8. So these are the graphs that you're dealing with. What are we interested in? We're interested in analyzing this data and get some information from this data. In your view, what is the mean of the data that you have? So let us take a look at our data here. We have all proportions. The percentage are on the horizontal axis. Starting from 0%, 10%, 20%, 30%, and so on. So the frequency that we have, it has the highest frequency, which is 250. So let us just label this here, 250. And this is the behavior of our graph, of our data sample proportions. We have the proportions here. Okay, 10% is around 200. Then we have 20%, which is, just move this line a little bit up. 15%, 250, 20%, again here, and then on 30% we have 50, okay, and for 4% it's very low. So this is the behavior of the graph that we see here. Question says, what is the mean of the data? How do we find the mean of our data? Remember that mean is called the balancing point. Mean or center or balancing point. What is the mean? Here on the horizontal axis, we have the proportions, and on the vertical axis, we have the frequency. What is the mean of the data? So as you remember, the mean or the balancing point is a number on the horizontal axis that balances this mass on top of it. It's going to be around here. This is our balancing point or the mean. It seems like it's around 16%. So 16% is representing the mean of the data that we have. And as you can see, your distribution is highly skewed to the right-hand side. The tail of the graph is on the right. The tail is on the right. So it is skewed to the right. If the tail was on the left-hand side, you say that it is skewed to the left. But since it is to the right, the tail is on the right-hand side, you say that, hey, the graph is skewed to the right. Well, the next question that I have for you is, what is the standard deviation here? Remember that when you have a data set, you're interested in knowing what is the center and also what is the variability. How do we calculate the standard deviation here? Let us go back to our simulation. Is there any information here in the simulation that we can use to answer the question about standard deviation? So by looking at our table here, we have the following information. It says, hey, the population proportion is 16%. This is the success. 1 minus P is called the error. 84%. N is the sample size, which is 20. N times P, we take P, we multiply it by N, we get 3.2. And N times 1 minus P, these are the criteria that we're going to talk about being normally distributed. Since these criteria, one of them is met, the other one is not met, we are just interested in taking more samples. The mean of the sample in the simulation is given to us as around 16%, and sample standard deviation is just right here. This small number, 8%, is our standard deviation. So the standard deviation, as you can see in the table, is 0.08 or 8%. This is our variability or standard deviation in this collection. That's how we read a table. Let's take a look at our note. The collection of sample proportions is part of the sampling distribution of all sample proportions from samples of size 20. Below are 4 dot plots of sample proportions similar to the computer simulation that we saw above. The dots are for sample sizes of 20, 40, 70, and 100. Note that each dot represents up to 4 data points. Match each data plot to its correct sample size. Think about how the sample size affects the spread of the sampling distribution. So let's take a look at the first dot plot. What is the sample size? When you are looking at this data collection, first we want to know how many data we had in this collection. The first dot plot. This is the second dot plot. This is the third dot plot. And finally, we have the fourth dot plot. See how it is. All of the values, all of the dots are jammed next to each other. So it means that it has the highest number of values in its collection. Dot plot number 4 has the most data in itself. It seems like you have 100. The sample size was 100. For number 3, well, we see more gaps between these dots. It means that comparing to number 4, we have less sample. It means that the sample size was around 70. For number 2, well, you can easily see the gaps between these bars, these dots. Well, the sample size decreases to 40. And finally, the first dot plot, which has sample size of 20. So as we saw, if we have more dots next to each other, if eventually we cannot distinguish the gaps between these dots, it means that we have sample of larger sizes, which is a good thing. In statistics, we are interested in having more data, taking more samples. It gives us a better result, more precise result. Let us move on to question 3. Think about how the distributions of sample proportions change in the dot plots above as the sample sizes increases from 20 to 100. Part A says, sample proportions are used to estimate population proportions. So we are using sample proportions to estimate population proportions. Remember that it's very hard to collect data about population. We need resources, we need money, we need people to collect data from the whole population. So instead, we are taking random samples and we find the characteristics for those samples, and then we make inferences and make estimates about population. Unfortunately, sample proportions typically contain error. because they do not include all data about the population. These are just random samples. How does the sample size tend to affect such error? If your sample size is just 20, you have more spread in the data, higher variability, higher error. If we increase the sample size, the graph is now just concentrated on one side, less gaps between your data. So you have less spread, less variability, or lower error. In statistics, we are interested in increasing the sample size. Why is that? Because we want to see lower error. If we have lower error, it means that we have a good information. We have good data, and then we can make an estimate about the population. As the sample size increase, we get a smaller error, which is a good thing because we can use this sample to make an estimate for the population itself. Question part B, does the distribution get wider or narrower with larger sample size? So as you can see, as we increase the sample size from 20 to 100, we have less spread, lower error, and a narrower graph. So the graph has more spread if the sample has size 20. More spread, higher variability, higher error, which is not a good thing. If it is increased to 100, the graph gets concentrated on one side. We have less spread, less variability, and a lower error, which is what we are looking for. And the graph gets narrower. Next question. We learned that the standard deviation of a statistic is called the standard error. So another name for standard deviation for a statistic is standard error. What happens to the standard error of the distribution of sample proportions as the sample size increases? So we are increasing the sample size. What happens to the standard error or standard deviation? As we increase the sample size, we get less spread or we get less variability. So we get less or lower standard error. So everything, as you increase the sample size, the rest of the bad information are getting smaller and smaller. Lower variability, less variability, lower standard error. Normal distributions are symmetric and well spread, with the mean at the center. Does the distribution of sample proportions become more or less normal as sample size increase? Well, take a look at your graph. This is the sample of sizes 100. We increased the sample size. And here you have a sample size of 20. Well, it's not very normal. It's not very bell-shaped. But as you can see, when we increase the sample size, it gets more bell or normally distributed. So again, as we increase the sample size, which is a good thing, we get a better shape for our graph, which is more normal. So graph seems to be normal as we increase the sample size. Now let us present the standard error formula. The central limit theorem. What does it tell us? When we are dealing with sampling distributions, either for the proportions or eventually for the mean, the central limit theorem says a sampling distribution of sample proportions from a population with proportion P is approximately normal, as we saw in previous graphs. It tends to be normal if you multiply n by p, it is larger than or equal to 10, and also the product between n and 1 minus p gives a number larger than or equals to 10. So what is n? N is our sample size. Remember that we are interested in having larger sample sizes, and P is the population proportion. If you multiply these two, you must have numbers larger than or equals to 10. If this is true, then central limit theorem says the mean of this new distribution, which we call the sampling distribution of sample proportions, the sampling distribution of sample proportion is denoted by, well, we have a new presentation. We write it as mu sub p hat. Mu sub p hat is called the mean of sampling distribution of sample proportions. Well, this new distribution has a mean. This mean is equal to the mean of the population. This distribution has a standard error. The standard deviation or standard error of this new distribution is denoted by, we represent that by sigma sub p hat, sigma sub p hat, which can be defined as, well, here we have algebra, square root of p times 1 minus p, all are inside the radical, divided by n. So we learned two new formulas today. First, we learned about this new distribution that we call sampling distribution of sample proportions. This distribution is just have a spread. This is like this. Here you have some dots representing the data in your collection. This is your distribution. And as we increase the sample size, we get less error. We have better approximation for the population. Well, again, this is your new distribution. When you have this new distribution, to any distribution, you can associate some characteristics, the center and the variability. The center of this new distribution denoted by mu sub p hat, which is the same as population proportion, and also the variability or standard deviation or standard error sigma sub p hat equals to square root of p times 1 minus p divided by n. Two important formulas. Let us take a look at one example. Let's do a little bit of calculation. So let's take a look at this example here. When a sampling distribution of sample proportions satisfies the normality criteria. What was the normality criteria? It's the properties that we are using in central limit theorem. N times p must be larger than or equals to 10. N times 1 minus p must be larger than or equals to 10. We can use the normal distribution properties to find probabilities or percentages corresponding to sample proportions. Well, we're going to do some calculations here. Consider the proportion of Republicans who worry a great deal about global warming, 16%, or P, the population proportion is 60%, which was reported in the Gallup survey. We want to think about how the shape of the distribution of sample proportions helps us identify the likelihood of various ranges of outcomes. In one random sample of 120 Republicans, 24 responded that they worry a great deal about global warming. So our job, our goal is to calculate the mean and the standard error for this new sampling distribution of sample means. Let us take a look at our board. Write down important information here. So what we learned that, first of all, when it comes to sampling distribution of proportions, central limit theorem says n times p must be larger than equals to 10, n times 1 minus p must be larger than or equals to 10. If this satisfies, then the mean of the new distribution, which is denoted by mu sub p hat, is equal to the population proportion. So the mean of the new distribution is equal to the population proportion. The standard error. The standard error of this new distribution is denoted by sigma sub p hat, which is the square root of p times 1 minus p divided by n. So in this example, what information are given to us? In this example, first of all, we know that p, or the population proportion, is 16%, 0.16. Write down important information. Explain what is this p represents. Population proportion. What else is given to us? Let's go back to our note. We have a sample of 120 Republicans. 24 responded that they worry about the global warming. So we have sample size n equals to 120. What is this? This is our sample size. So let us stop. We have some formulas related to these two numbers, p and n, in central limit theorem. The criteria for normality says np must be larger than equals to 10. N times 1 minus p must be larger than equals to 10. So let us do some calculation. Let us do the algebra. Okay. We need to calculate n times p. 120 times 16%. We also need to calculate n times 1 minus p. 120 times 1 minus 16%. So if you multiply these two numbers, the result is 19.2, which is larger than or equals to 10. So it is checked. It's checked. So we can go and check the second multiplication. What is n times 1 minus p? As you computed it, it is 100.8, which is larger than equals to 10. So what do we say? We say that, hey, the normality is met. We are happy about the criteria for normality. We have those criteria. So now we are allowed to go and calculate the mean and the standard error. So the central limit theorem gives me this information, gives me this confirmation. It says, hey, since, you write down, since the normality is met, we have the following. The mean of the sampling distribution of the proportions is mu sub p hat, which is equal to p. What is p? Well, p is given to me here. P is 16%. Just copy down 16% or 0.16. Finding the mean is very easy as long as you have the population proportion, you just copy that here. The rest of the calculation. So I found the mean. Let us check the mean. Now we need to find the standard error. The standard error, E or standard error of the sampling distribution of the proportions is sigma sub p hat, which is, well, I have to do a little bit of calculation. The square root of, well, here I have P1 minus P divided by N. So let us plug these values in the radical and do the calculation. We get square root of, well, I have 16%. 1 minus 16%, all inside the radical, divided by N. What is N? N is 120. I already wrote down important information here. N is 120. So what is sigma sub p hat? Approximately. So our standard error is 0.033.034. This is our standard error. So we found all the information that we need for this new distribution. But how do we represent this new distribution? So far we learned that P, or the mean of this new distribution, is 16% or 0.16. We found the standard error, which is approximately 0.03 or 3%. What is the next step? In our next step, we want to visualize this distribution. How do we visualize this distribution? Central limit theorem says, hey, it's almost a normal distribution. So it means that the graph of the distribution can be written this way. So let us have our graph here. It's a normally distributed graph. On the horizontal line, we're going to have the percentages, the proportions, and on top, it forms the frequency of each bar that we saw before. First of all, since it's a normal distribution, the mean is in the center, the balancing point. But what is the mean? We found the mean to be 16%. So mu sub p hat, which is 16%, is just right in the middle. Now, based on what we learned before, we can divide up this distribution into some scales. In the right-hand side, we have mu sub p hat, plus 1 standard error, sigma sub p hat. If we move along, we get mu sub p hat plus 2 sigma sub p hat. And on the far right, mu sub p hat plus 3 sigma sub p hat. So 16% plus 0.03. 16% plus 2 times 3%, which is 6%. 16% plus 3 times our standard error, 9%. So on the right-hand side, we have 16%, we have 19%, we have 22%, we have 25%. So we can divide up the graph this way. In the middle, the balancing point is 16%. Then we scale that using the standard error, 19%, 22%, 25%. As you can see, it's toward the values that are on far right tail of the graph. The same for the left-hand side. For the left-hand side, we just subtract. We have mu sub p hat minus 1 standard error. Mu sub p hat minus 2 standard error. And finally, mu sub p hat minus 3 standard error. So here we have 16% minus 3%, 16% minus 6%, and 16% minus 9%. This gives me 13%. This gives me 10%. And here I have, well, 7%. So this is our normal distribution. Empirical rule for the normal distribution. 2 standard deviations around the mean. Remember that. 1 standard deviation away from the mean. These are the information that we learned before. Here we can divide up the percentages below the graph using the empirical rule.